Okay, so in this video, we want to consider a heuristic argument as to why it is natural to consider functions, real functions, as vectors. If you remember, what we have used initially is that the space of all real functions satisfies the 10 axioms of a vector space, and for that reason, the space of all functions on the reals is a vector space, so we can think of functions as vectors. This is not very intuitive, so let's give a much more heuristic, much more intuitive argument as to why it is natural to consider functions as vectors. Let's go back to R2. R2 consists of all vectors in the plane, and therefore vectors with two components, x1, x2, where x1 and x2 are allowed to range over all possible real numbers. Well, if you think of this, what you have here is an assignment of real numbers. To 1, the positive integer 1, we assign the value x1. To the positive integer 2, we assign the value x2. So what we have is an assignment of values. Well, that is simply a function. To the real number 1, we assign x1, therefore f of 1 is x1. And to 2, we assign the value x2, that is f2. So we have a function defined at only two real values at the first two positive integers. And so you can now view this vector in R2, which is a directed line segment, as the graph of a very simple function that is only defined on the first two positive integers, 1 and 2. And the value assigned at x equals 1 is x1, say this value. And the value assigned at x equals 2 is f of 2, which is the second coefficient of our vector. And so you see, quite naturally, you can think of a vector in R2 as not only a directed line segment in R2, but as a real function defined only on the first two positive integers. F of 1 is the first term of your vector. F of 2 is the second term of your vector. Well, let's look at R3 now. Right? We can naturally extend the idea of vectors in R2 to vectors in R3 by adding quite simply a third component to our vectors. And now what we have is an assignment of three real values. To 1, we assign the value x1. To 2, we assign the value x2. And to 3, we assign the value x3. So now we can think of this vector in R3 as a function defined on the first three positive integers. x1 is the first value of our function at 1, x2 the second value of our function at 2, x3 the third value of our function at 3. And so now you can think of this vector as a slightly more complicated function defined on the first three positive integers. So at 1, the value is f1, which is the first coefficient of your vector. At 2, the value is f2, the second coefficient of your vector. And at 3, the value is f of 3, the third coefficient of your vector. And so you see, you can naturally think of a vector in R3, a vector with three components, as the graph of a function defined only on the first three positive integers. And we can keep going. Let's look at R4. We can naturally extend R3 to R4 by adding a fourth component to our vector. And now we have an assignment of four values. To 1, we assign x1. To 2, we assign x2. To 3, we assign x3. And to 4, we assign x4. And so we have four values of a function at 1, 2, 3, and 4. So if we visualize the graph of this function, it will be a little more complicated. It will be the graph of a function defined only at the first 4 positive integers. And again, the value of the function at 1 is simply x1. The value of the function at 2 is simply x2. The value of the function at 3 is simply x3. And the value of the function at 4 is simply x4, the fourth coefficient of our sequence, of our vector. And so you see, very naturally, a function defined only on the first 4 positive integers, so a very simple graph with only 4 points, is a vector with 4 components. And you can keep going. We can look at R5, R6, R7, up to R infinity. Let's consider now vectors with an infinite number of components. And this is where things get a bit more interesting. So R infinity is the set of all vectors with an infinite number real vectors, so the real coefficients. But now we have an infinite number of coefficients, x2, x1, x2, x3 up to infinity. And once again here we have an assignment of values, but an infinite assignment of values. To 1 we assign x1, to 2 we assign x2, to 3 we assign x3, to 4 we assign x4, and so on. And so we now have a function defined on all positive integers. And we can again visualize the graph of this function that will again give us a different way of thinking about our vector with an infinite number of components. So we can now think of this vector as the graph of a function defined only on all positive integers. And again, the y values are the coefficients of our vector. So the first y value at 1 is the value x1. The second y value at 2 is x2, and so on. The y value at 3 is x3, the y value at 4 is x4, the y value at 5 is x5, and so on. And so you see quite naturally, a vector with an infinite number of components is simply the graph of a function defined on all positive integers. So we can now write R infinity in a more interesting fashion. R infinity is the set of all vectors with an infinite number of components where the xi's are allowed to range over all real numbers, but now we have just looked at a different way of thinking about a vector with an infinite number of components. It is the same as a function defined on all positive integers. So you see R infinity, the set of vectors with an infinite number of components, is simply the set of all functions whose domain is the positive integers. So when you visualize this as functions, you would look at graphs of functions where you only have a discrete number of points for each positive integer. And this is where it's interesting. This is the first time we now view a space of functions as a space of vectors, right? Quite naturally, R infinity is a space of vectors, but where the vectors have an infinite number of components. So this is quite naturally a vector space, but the set of all functions from the positive integers to the real numbers is equal to R infinity. So quite naturally, the space of all functions defined on the positive integers is a space of vectors. They are vectors with an infinite number of components. So this is naturally a vector space. So we can think of functions defined on the positive integers as vectors. Vectors with an infinite number of components. And then you can ask quite naturally, well, why stop there? If we can think of functions defined on the positive integers as vectors, why not consider the continuous analog? What if we now link these points in a continuous fashion and have the graph now of a more complicated function? We can still think of this function as a vector, simply by extending the domain from the positive integers to all real numbers. So if we take all functions now from the real numbers to the real numbers, it is not much of a stretch to think of this as a vector space, because the set of all functions defined on the positive integers is a vector space. It is the vector space of vectors with an infinite number of components. So naturally, if we just extend the domain from the positive integers to all real numbers, what we have is the continuous extension of this vector space. And so naturally, the space of all functions from the reals to the reals is naturally a vector space. So hopefully now the idea of thinking of functions defined on the real numbers to the real numbers, thinking of these as functions is more natural, right? We no longer think of it as, okay, because functions satisfy all of our 10 axioms, they form a vector space and we can think of them as vectors. That was not so intuitive, but hopefully with this argument you can now see that quite naturally, because all functions from the positive integers to the reals are simply vectors with an infinite number of components. It is not much of a stretch to look at the continuous extension of these vectors, of these functions, from the reals to the reals. And this is why I claim that it is natural to think of functions from the reals to the reals as vectors. Therefore, this being a vector space. So hopefully, this gives you a better sense of why this is a natural idea, that functions are also naturally vectors.